video 6D, and we are starting in the book on page 171, where it says, using chemical equations when the limiting reactant is identified. So back to talking about the limiting reactant. The limiting reactant is the reactant that is not in excess. Of course, in excess means that there's more than enough. So if there's more than enough of one reactant, that's not going to limit the reaction. It's going to be the other one. So you will normally have a limiting reactant and then a reactant that is in excess, or maybe even a couple reactants that are in excess. Also under the limiting reactant, we have to point out that then you use the quantity of the limiting reactant to calculate the quantity produced. Okay, so in a chemical equation, if there is one reactant that is in excess, we're not going to worry about how much of that we have because we know that we have more than enough of that one. We're going to use the amount of the limiting reactant. That is going to determine how much product can be produced. So we use the quantity of the limiting reactant in our problems. Let's try an example. Take a look at example 6.4. It is on page 172. I will read it. Some ores contain a small amount of precious metals that are in compounds with many other elements. For example, one common ore found on Earth is KAgC2N2. Since silver, Ag, is a precious metal, it is useful to be able to extract silver from this ore. The following reaction accomplishes this task. Let's write the reaction out. We have 2 KAgC2N2 plus the other reactant is zinc, Zn, yields 2Ag plus Zn C2N2 plus KCN. Okay, I just copied the balanced equation from the example. And the question is, if a chemist adds 1.61 moles of KAgC2N2 to excess zinc, how much pure silver can be made? Okay, so we know, or let's see, first we're going to write down what we're going to find. Find how many moles of silver are produced. And what we know is, what did it say was in excess? Did it say the zinc was in excess or the iron ore? That's right, it said the zinc is in excess, which means we have more than enough of zinc. So the limiting reactant, Lr, equals the KAgC2N2. So that's the quantity that we're going to use in order to determine how much silver can be produced. This is very similar to the problems that you guys have already done. It's just worded a little differently so that you can identify the limiting reactant. Okay, so we have 5.61 moles of the limiting reactant, KAgC2N2. And then let's also write down the ratio for that reactant. It says for every 2 moles of KAgC2N2, we can produce 2 moles of silver. So I can tell by looking at it that it's a 2-to-2 ratio, which is a 1-to-1 ratio. So however much KAgC2N2 we're starting with, since it's a 1-to-1 ratio, we're going to produce that same amount of silver. But I'm going to write it out for you anyway. So we have 5.61 moles of KAgC2N2, and we're going to multiply it by the ratio. Okay, using the factor label method, the units we want to get rid of go on the bottom. So moles of KAgC2N2 go on the bottom, and we are looking for moles of silver, so that goes on the top. And then we plug in the numbers. Remember, there were 2 moles of KAgC2N2 for every 2 moles of silver produced. So if you plug this into your calculator, you would put in 5.61 times 2 divided by 2, and you would get 5.61 moles of KAgC2N2. And we would circle our answer. And here comes my special helper. I will be right back.
Mommy.
Okay, my special helper is again happily watching Netflix. So off we go. The next thing for video 6D will be to talk about Gay-Lussac's law. Gay-Lussac's law states that the stoichiometric coefficients in a chemical equation relate the number of moles of gases. We've already talked about how they relate the number of moles. And they relate the volume in liters for gases. So that's the new part. If we are talking about just gases, and you can see that in the parentheses of the chemical equations, if we're talking about only gases, not only do the coefficients out front tell you the number of moles for each gas, they can also tell you the number of liters, the volume of the gases. So write that definition down. We'll also point out this beautiful adjective that I used up here, stoichiometric. Coefficients, just the same as the coefficients that we've always been referring to, those big numbers out front of the chemical formulas in the equations. But now that you know the term stoichiometry, we can use that beautiful adjective, stoichiometric coefficients. So write that definition down. A few more important notes about this law. All the numbers involved in your problem, when you go to do your factor label method, that is, all the numbers involved in your factor label method must be in either moles or liters. You can't be using moles here and then liters here. Okay, it has to either all be in moles or all be in liters. Because, next point, you cannot convert from moles to liters. Okay, for the Gay-Lussac law, it needs to all be in moles or all be in liters. You can't convert from one to the other. And for the Gay-Lussac law, all the substances in your problem must be gases. This does not work for solids or liquids. It's only gases. Let's try an example. All right, example 6.5. An automobile engine burns gaseous octane, C8H18. If an automobile completely combusts 12 liters of gaseous octane in excess oxygen, how many liters of carbon dioxide will be produced? Isn't it cool that we can figure out just how many liters of carbon dioxide is produced in that engine? Let's just ponder that for a moment. Pretty cool. All right, so the first thing that you have to do in any stoichiometric problem is, of course, come up with a balanced equation. So I wrote down the balanced equation here because we have had several opportunities for practice of balancing equations. So I didn't do that for you on the video. So we have 2C8H18, which is a gas. Now it's important to notice because we're talking about liters, so we have to know if things are gases. That's a gas. All of them are gases. Plus 25O2 gas, plus, yields 16CO2 gas, plus 18H2O, also a gas. So because everything is gases in this problem, we know that we can use either moles or liters. And in this problem, we are looking for number of liters. So let's write down what we're looking to find. The problem says to find liters of carbon dioxide. How many liters of CO2? What do we know? What's the limiting reactant? The limiting reactant is the one that's not in excess. The problem told us that oxygen was in excess, so the gaseous octane must be the limiting reactant. And it told us how much we have of it. We have 12 liters. 12 liters of C8H18. Okay, so we are going to be converting from this octane to carbon dioxide. Let's write down the ratio that we know we have. For every 2 liters of CH18, you see how normally we do moles, but when they're both gases, we can also do liters. So for every 2 liters of C8H18, we can produce 16 liters of CO2. And remember, you have to keep it all in liters for the problem, and they both must be gases, the two that we are going to be converting between. Okay, so we're going to start with 12 liters of CH818, and we're going to multiply by our ratio. We have liters of C8H18 on the bottom. We have liters of carbon dioxide on the top, and now we plug in our numbers. There were 2 liters of C8H18 for every 16 liters of CO2 produced. Put that into your calculator. You'd put 12 times 16 divided by 2, and the answer is 96. 2 significant figures. And our answer will also be in liters. These two cancel out. Our answer is 96 liters of CO2. So that is how you would apply Gay-Lussac's law. When you have gases that you are converting between, you can use liters or moles. That's Gay-Lussac's law. And that is video 6D.